Dear participants, the EFFECT team warmly welcomes you to this third module on using quasi-experimental methods in real-world education settings. After successfully completing this module, you should be able to present alternatives to RCTs and know what to do if RCTs are not feasible. You should further know the differences between quasi-experimental methods. Therefore, the purposes of this module are to present you some alternatives to RCTs, present the differences between these methods, and learn how to interpret empirical findings from these methods. Dear participants, welcome to submodule 3.1, in which we will define what we actually mean by quasi-experimental. Quasi-experiments fulfill the following criteria. They do a causal impact evaluation and are based on a comparison on treatment and comparison groups. However, contrarily to RCTs, no random assignment happens in quasi-experiments, which is a fundamental distinction with experimental methods such as RCTs. Dear participants, welcome to submodule 3.2, in which we will motivate the use of quasi-experimental methods. We will have a look at why we actually use quasi-experimental methods. Indeed, we might ask ourselves, we have spent the whole module 2 studying the implementation and use of randomized control trials, which actually aim to estimate a causal impact. So why do we need quasi-experimental methods, which can do exactly the same thing? The use of quasi-experimental methods is actually motivated by the fact that RCTs can face numerous constraints, which can hinder the implementation of an experimental setting. Imagine the following case. The impact of a potentially helpful remediation program in primary school should be evaluated using an RCT in a socially disadvantaged primary school. In this case, some pupils, those in the treatment group, would benefit from the intervention, while some other pupils, those in the treatment group, would not benefit from the intervention. This situation can lead to many ethical, political, and legal dilemmas. For example, what would justify that a given student should have access to a given remediation program, whereas another student, the one in the control group, should not have access to it? Legal, political, and ethical principles of equal treatment would indeed require that all pupils should have access to the treatment, which would then undermine the identification strategy. If no control group exists, then the impact cannot be attributed to the intervention. Another type of constraint can be the logistical constraints. Imagine that we have a very large number of participants in a study and cannot perform the study at the same time. These are some reasons why quasi-experimental methods can be very useful. Dear participants, welcome to submodule 3.3, in which we will shed light on the difference between a randomized control group and a non-randomized comparison group. First, let's highlight the common point between RCTs and quasi-experimental settings. Both impact evaluation techniques compare a treated group with a non-treated group to determine the impact of a program, an intervention, a policy, etc. However, there are also some huge differences between RCTs and quasi-experimental settings. Whereas in RCTs, treated and non-treated groups are randomly allocated, in quasi-experimental settings, such treated and non-treated groups are not randomly allocated. In RCTs, we call the non-treated group a control group, whereas in quasi-experimental settings, we call the non-treated group a comparison group. It should be highlighted in this context that the word control group implicitly assumes a random allocation of the non-treated group, while the word comparison group assumes a non-random allocation of the non-treated group. Therefore, the term control group should only be used in the context of RCTs, whereas the term comparison groups should only be used for quasi-experimental settings. Dear participants, welcome to submodule 3.4, in which we will start to discuss non-randomized difference in differences. As you know, we have first discussed difference in differences as a measurement technique to assess the impact in RCT settings. However, we can also apply difference in differences without having previously randomized, which then provides a so-called non-randomized difference in differences. The underlying method of a difference in difference, even if it is non-randomized, remains the same. we have 4 points of observations, which are the comparison group before the treatment, the comparison group after the treatment group before the treatment, and the treatment group after the treatment. And each time in the regression, we will add one variable which will capture each possible state, each possible point of observation. And again, beta 3 will end up being the difference in differences, the effect that occurred only in the treatment group and only after the treatment, which will then be the effect of the treatment. Dear participants, welcome to submodule 3.5, in which we will discuss non-randomized difference in differences, and more precisely the regression that can be used to estimate it. As you can see, the regression that we use here is exactly the same as the regression we presented in module 2. Again, we have the observed phenomenon for observation I at moment t, which is noted yit. Again, we have all the other control variables which are included in the regression, which is noted beta times x. And again, we have the small epsilon that captures everything that cannot be explained by the explanations we already have. In this context, I would just like to highlight that beta times x is a vector notation. This is not very important, but it's actually a short notation to note beta times the control variable plus beta times the second control variable plus beta times the third control variable, and so on and so on. It's just a short notation. It seems more difficult than it actually is, and it is not that important in this context. We again have a time variable after, taking value 1 if the observation was taken after the intervention, and we again have a treatment variable treated, taking value 1 if the observed individual was in the treatment group. So as you can see, the regression which would be used to estimate the impact of the intervention would still be the same regression than the one we used to analyze the impact of an RCT. The difference would not lay that much in the technical analysis, but in the way the observed values have been created. Instead of creating treatment and comparison groups randomly, the treatment and comparison groups are created non-randomly. And it should, however, be ensured that the treatment and comparison group are comparable prior to the intervention. We will come back to that. But the most important thing in this context is that not the technical analysis changes, but the way in which the treatment and control groups are constituted. Dear participants, welcome to submodule 3.6, in which we will continue our discussion on non-randomized difference in differences and advance to more graphical analysis of a difference in differences approach. This slide shows a typical graphical representation of difference in differences. As you can see, the difference lies mainly in the slope. If we assume that both groups are comparable at the onset of the study, then there is no other possible explanation than the one that it was indeed the intervention that caused the difference between the different patterns and the different outcomes. Both groups are comparable at the start of the study, so why should one of the two groups start to deviate from its pattern and, in this case, have a sharper increase than the other one? If the treated group was not treated, then it should have just followed the counterfactual pattern. But as you can see, it did not. It had a sharper increase. And this actually shows that the treatment that has been analyzed in this graphical representation actually had an effect compared to the non-treated group, which shows the pattern that the treatment group should have followed if it did not follow the intervention. Dear participants, welcome to submodule 3.7, in which we will discuss the general idea behind matching techniques. The main underlying idea behind a matching technique is that one treated and one non-treated observation are put in pairs and then compared. They must be identical in every aspect besides the treatment, which is the main general idea behind the matching technique. However, it is quite difficult to perform a perfect matching technique because it is nearly impossible to get one treated and one non-treated observation which are identical in every aspect besides the fact that one was treated and the other was not treated. We will address this problematic in the following submodules. Dear participants, welcome to submodule 3.8, in which we will start to discuss propensity score matching. First of all, what is a propensity score and how is it computed? A propensity score is based on observable characteristics. Based on these characteristics, a probability is computed to participate in the treatment. So based on what we can observe, we actually compute a probability of an observation to be treated or not. And this probability is then called the propensity score. What now happens is that we do the matching actually based on the observation's propensity scores. This means that an observation with a given propensity score that experienced the treatment is matched with an observation with a similar propensity score that did not experience the treatment. As the propensity score is based on observable characteristics, the propensity score can be seen as some kind of a proxy for the characteristics of the different observations. Dear participants, welcome to submodule 3.9, in which we will continue to discuss propensity score matching. As for the non-randomized diff and diff, you can see on this graph a more graphical representation of how propensity score matching works. As you can see on the graph, treated and non-treated units are matched, and as we have discussed during the previous submodule, the matching happens based on the unit's probabilities to benefit from the treatment, which we call the propensity score. Dear participants, welcome to submodule 3.10, in which we will continue our discussion of propensity score matching. Today, we will have a look at an academic article which uses propensity score matching, namely the article Assessing Regional Performance Against Early School Leaving in Spain, written by Dr. Bayon Calvo, Dr. Corrales Herrero, and Professor De Witte, who found that differences in early school leaving in Spain can be attributed to different population characteristics, but also in 3 regions to the educational policy. Indeed, early school leaving is found in the literature to be influenced by macroeconomic and social contexts, and therefore, Dr. Bayon Calvo and his colleagues define groups or clusters of regions based on the youth unemployment rate, which is a macroeconomic variable, and education and poverty metrics. Based on the previously defined groups, Dr. Bayon Calvo and his colleagues define a propensity score for each individual observation. An individual that left school, which corresponds to a treatment in this context, is then matched with an individual with a similar propensity score in the control region. Dear participants, welcome to submodule 3.11, in which we discuss regression discontinuity design. In which context should this technique be used? Sometimes treatments occur from a given threshold on, and in such cases, an observation counts as treated once it passes a given threshold, but then, once an observation gets closer to the threshold, its characteristics are not that different from the treated observation anymore. And regression discontinuity design uses exactly this aspect, as the observations which are very close to, but still below the threshold, become comparable to the treated observation, they can be used as a valid comparison group. This graphical explanation reports the main idea. As you can see, there are 2 different regression lines, one for the non-treated group and one for the treated group. And as you can further see, these 2 regression lines are different and even discontinuous. And that's actually what indicates an impact. If we have 2 different regression lines, then one could say that we have actually 2 different samples. But when do we have 2 different samples? If the treatment has an impact, if we base ourselves on the assumption that the groups were comparable at the beginning. And therefore, as we have 2 different samples, the treatment had an effect. Dear participants, welcome to submodule 3.12, in which we continue to discuss regression discontinuity design. Today, we will discuss a case study using regression discontinuity design, namely the article The Effect of Funding for Disadvantaged Students on Academic Underachievement, published by Dr. Oleg Badunenko, Professor Denis Mazrekesh, Professor Zubal Kumbakar, and Professor Christoph De Witte, who found that additional funding for schools with disadvantaged students has an impact on academic underachievement. In the article, the researchers analyzed the Equal Educational Opportunities Policy in Flanders, which was implemented in 2002. Based on 4 criteria, the Flemish Ministry of Education determines a share of students from disadvantaged backgrounds, and if this share exceeds 10%, the school gets additional personal funding. Dear participants, welcome to submodule 3.13, in which we continue our discussion on regression discontinuity design. Let's get back to our case study, namely the article published by Dr. Badunenko and his colleagues. As has been previously discussed, the determination of a causal impact using a regression discontinuity design requires a threshold, but the GOK policy uses such a threshold, namely the 10% threshold of disadvantaged students, and therefore this threshold captures the difference between treated and non-treated observation and can therefore be used for the regression discontinuity design. This is the regression used by Dr. Badunenko and his colleagues to estimate the impact of additional funding due to the GOK policy. D is a binary variable, which is equal to 1 for the treated sample and equal to 0 for the non-treated sample, whereas CIT is the share of disadvantaged students in one school. It should be highlighted in this context that if D equals 1, then both the intercept and the slope of the regression equation are completely different. This means that if there is indeed a significant treatment effect, we should observe two different lines in the graphical representation. Dear participants, welcome to submodule 3.14, in which we will start to discuss synthetical comparison groups. Sometimes it might happen that a treatment, for example a policy, is applied to a whole territory, for example a region, at the same time. This allows on the one hand to make the whole territory benefit from the policy intervention at the same time, but it also implies that there is no comparison group if we want to evaluate the policy afterwards. To be able to nevertheless conduct a policy evaluation, a so-called synthetical comparison group can be used, which can be explained as a weighted average of different non-treated territories, which, taken together as a weighted average, show the same pre-treatment characteristics as the treated territory. Dear participants, welcome to submodule 3.15, in which we continue our discussion on synthetical comparison groups. Let us consider the following fictional example. Imagine that in a region, an awareness campaign is introduced to reduce smoking among underage pupils in secondary school. Imagine further that in this region, prior to the policy's implementation, 5% of underage children smoke. The issue here is straightforward. As the policy is applied to the region all at once, there is no apparent comparison group available which could be used for an ex post policy evaluation. To solve this issue, we can create a synthetical comparison group to have a counterfactual, which means a modeling of what would have happened if the policy had not been implemented. In this context, we choose region A, in which 11% of underage pupils smoke, region B, in which 2% of underage pupils smoke, and region C, in which 7.25% of underage pupils smoke, and we assign the following weights. Region A gets a 10% weight, region B gets a 50% weight, and region C gets a 40% weight. If now we compute the weighted average of these three regions, we arrive at 5%, which means that we created a synthetical equivalent of our region of interest, which can now be used to simulate a non-treated scenario. Dear participants, welcome to submodule 3.16, in which we continue to discuss synthetical comparison groups. So far, we have created a treatment group and a synthetical comparison group, which were comparable prior to the treatment. Using the synthetical comparison group, we can simulate what would have been the trajectory of the treatment group if the treatment did not happen. At the same time, the observations obtained from the treatment group allow to determine what happened following the treatment. Since we now got observational data for the treatment group, which means data based on what actually happened, and simulated data for the synthetical comparison group, which means data based on the simulation, we can actually perform a difference in differences to estimate a causal impact. This difference in differences is estimated using exactly the same modus operandi as before, and again, beta 3 is the difference in differences, the effect that occurred only in the treatment group and only after the treatment. Dear participants, welcome to submodule 3.17, which will be the last submodule on synthetical comparison groups. Today, we will apply our knowledge on synthetic comparison groups on the article The Effect of School District Nutrition Policies on Dietary Intake and Overweight, a Synthetic Control Approach, published by Dr. Sebastian Bauhoff, who found that a policy on food and beverages introduced in Los Angeles was mostly ineffective to reduce the prevalence of overweight students. What Dr. Bauhoff actually did was to mix several control regions in order to build a synthetic comparison group, such that similar results are obtained for relevant variables, such as the BMI Z-score, which is a common measure for overweight. Dear participants, welcome to submodule 3.18, in which we will discuss what a random phase-in is. To do so, let's come back to ethical issues. At the end of module 2, we have discussed potential ethical dilemmas of RCTs, including the dilemma that some participants might not be able to benefit from the treatment. The random phase-in method can help to solve this dilemma. In this example, we have created 4 randomized treatment groups, with each group receiving the treatment at different moments in time. This allows that the first group, which is treated first, can use one of the 3 later groups as a comparison group or a mix of them, while the second group can use group 1, 3, or 4 as a comparison group, and so on. The idea behind this is that there should always be one group which is sufficiently untreated to be used as a comparison group. Sufficiently untreated means in this context that even though each group is treated at a given moment, group 1 could, for example, be used as a comparison group for group 4 when this group is treated, provided that the effect of the policy has sufficiently faded away. This is the main mechanism of a random phase-in. On this slide, you can see the sources that have been used to build up this third module. The effect team thanks you for having completed module 3. If there are any remaining questions, suggestions, etc. regarding this module, please contact Professor Dr. Christoph de Witte, who is the main coordinator of EFFECT and the director of the Lehr Research Group at KU Leuven.